In a previous podcast, we have seen how analytical solutions can be developed for horizontal infiltration in homogeneous soil. We also introduced the sortivity as a specific property that allows to model the horizontal infiltration process. In this podcast, we analyze the vertical infiltration, and this for a linear and a green and ant soil. For the vertical infiltration in a linear soil, we obtain the following form of the Fokker-Planck equation. The first term, with the diffusivity, refers to the capillarity driver of the flow. The second term refers to the gravity driver of the flow. This is a nice equation that we will analyze more in detail in the chapter related to chemical transport in the soil. As a matter of fact, if we replace the theta with c, the k with v, pore water velocity, and d with hydrodynamic dispersivity, we obtain what is called the convection dispersion equation, which is the governing equation for describing chemical transport in soil. We'll come back to that later on in the course. So if we take this form of the vertical flow equation and we subject them to the boundary conditions and the initial conditions which are referred here, we can obtain an analytical solution for describing the water content profile in soil. The demonstration applies again the transformation of the transport equation in the Laplace domain and an inverse Laplace transform. The equation is given here in terms of SE, the saturation degree, and in terms of the hydraulic properties K and D. The equation allows to simulate the soil moisture profile at any depth Z and any time T. As with the horizontal infiltration, an error function appears in this analytical solution. If we subject the soil to a flux type or a Neumann boundary condition, then we find a solution as shown in this equation. Again, it is an analytical solution that depends on the soil parameters K and D and the values imposed at the boundary of the system, in this case GW. We consider that GW, the flux, is smaller than saturated conductivity of the soil. We can of course use the analytical solutions to calculate the water content profile as a function of time and integrate this as a function of depth in order to obtain the cumulative infiltration as a function of time. With this we can subsequently calculate also the instantaneous infiltration rate as a function of time. All this is illustrated in a Python notebook script that we invite you to analyze after this podcast. Now we have seen the solution for a linear soil. Let's move to the solution for a green and ant soil. As in the case of the horizontal infiltration, we consider in a green and ant soil that the water transport follows a kind of piston flow concept. In front of the wetting front, the soil is at its initial water content theta I. Beyond the wetting front, the soil is nearly equal to the saturated water content, or it's equal to theta 0. If we consider that the Dirichlet boundary condition is imposed, then theta 0 will be equal to the saturated water content theta S. As in the horizontal case, we can formulate the infiltrating flow rate using the mass conservation equation and the Darcy equation. For this latter equation, we need of course to consider a contribution coming from both the capillary driver and the gravity driver. The combination and integration of this equation allow us to calculate T as an expression of LF, the position of the wetting front. Subsequently, we can use again the mass balance equation to express the solution in terms of the cumulative infiltration I. This is the green and ant solution of the infiltration problem. It is a bit a strange formulation since it gives the time as a function of LF, and this in terms of the soil properties K0 and initial boundary conditions theta 0 and theta I. Normally you write LF as a function of T, but in this case we cannot analytically invert the solution to obtain LF as a function of T. We therefore have what is called an intrinsic solution of the infiltration problem. We also need to define more clearly how we can calculate HF, the suction head, at the wetting front. Actually, in the green and ant model, we deal with a mathematical singularity at wetting front, which complicates the definition of HF. In front of the wetting front, HI may be very large, very negative, while beyond the wetting front H0 may be very small, 0 in the case the soil is saturated. So, within an infinite small soil layer at the position of the wetting front, the suction head changes from very large to very small. To solve this problem, soil physicists introduce a weighing mechanism to define the suction head at the wetting front between the very large and the very small suction heads before and after the wetting front. They suggest to use either the conductivity or the diffusivity function to make this weighing. This is explained more in detail in the following Python notebook. So, we've seen in this podcast some analytical solutions of the infiltration problem in the linear and the green and AND soil. We invite you now to have a look to some Python notebooks where these concepts are implemented more in detail.